section 14.2. Again, this is in your math lab, section 13.2, but 14.2 in the book. And so we've been talking about reflections in this section, and the idea of a reflection is that you simply are flipping an object across a line. Okay, and that line may be just some arbitrary line, or it may be a specific line that we have designated. So when we talk about flipping across this line, a lot of times we can do that in the coordinate plane or in the coordinate system. And so some common lines that we would use would be the x-axis. So if you're thinking about the coordinate plane, the x-axis is the one that runs right and left. That's this one. The y-axis is another common one. That's the vertical axis. And then this line that goes through the origin with a slope of 1, which is the equation y equals x, that's also another common line that we use as lines of reflection. So we may, for example, back up, we may take some object down here and flip it across this line to where we have the same object over here, but we have flipped it. Okay, and so when we talk about this reflection across this axis or across a line, those are three common ones that you may see. Okay, so with that in mind, look at this example, and this is just strictly an illustration to kind of show you how flipping across this y equals x line would work. So if we start with the point 1, 4, that's this one up here at the top, and we reflect it across the y-axis. I'm sorry, not the y-axis, the equation y equals x. Then what's going to happen is the distance from that point to this line is going to be the same as it is from our new point, A prime, to that line. And remember, this line of reflection is a perpendicular bisector. So that means that the line between our 2 points is perpendicular to this line of reflection, and it bisects it. So this distance is the same as this distance. Okay? And so that's really important when we talk about reflecting across a line, because if we know this point and we know this point, so A and A prime, then we could actually figure out what the line of reflection is by finding the midpoint of the segment between those. And in other classes, algebra classes, you've learned about midpoint. It's a pretty easy formula, basically finding the average of your x's and average of your y's. And you can easily find some points that will be along this line, this y equals x line, and you could actually draw that line if you needed to. And so the same thing is true with this other group of points. Point B is negative 3, 0. And again, when it's reflected across this line, this distance is going to be the same to B prime. Okay, so that distance is the same. And again, it's going to be perpendicular. And so this idea of reflection is simply taking it across, flipping it across that line. Okay, and so as we talk about reflections, it's important you understand that the distance from each vertex to that line of reflection is the same, and it's also perpendicular. Okay, so that's going to be something that is going to help you as you're working through your math lab, for example. There may be a question where we ask you, what is that line of reflection? Well, if I ask you for that, you're going to take this ordered pair and this ordered pair, find the midpoint, which is this x sub 1 plus x sub 2 over 2, and y sub 1 plus y sub 2 over 2. And you figure out that ordered pair, and that's going to give you this point. Okay, the midpoint between those. You can do the same thing with the other 2 points, and you would get this point. And then connect that line, and you would have the line. I don't think I'm going to give you that, but there are some examples in your book that I have noticed that are similar to that. We're not going into tons of detail there because I don't anticipate giving you one of those. But I do want you to know that is a possibility, something that you could do if you needed to. If you have any questions about that in the coordinate system, definitely let me know. Now, let's talk about some real world application. So you have probably at some point been driving down the road or riding with somebody down the road, and you or somebody else has their phone sitting in your lap on a sunny day, and the sun has reflected off your phone and into your face, into your eyes. I know that's happened to me multiple times. I'm sure that's happened to you at some point. And when that happens, there are some angles involved, okay? And so we get a reflection. We're getting a reflection off our phone. You could do the same thing with a mirror or any other object that would reflect that light. But what's happening is you have the sun here, and it reflects a light, or reflects the sunlight, down to an object. You could have your phone, you could have a mirror, you could have a number of things. And then that light bounces off of that phone, mirror, whatever it is, back to where you are, maybe your eyes or your face or whatever, okay? And so when that happens, we have some geometric properties that come into play. Number one, we have what we call an angle of incidence. So from where that sunlight hits your phone at that point, if you drew a vertical line up through that point, and then use the ray from the sun and this vertical line, that forms an angle, and that angle is called the angle of incidence. Now, the measure of that angle of incidence is the exact same as the angle of reflection. So the angle of reflection is found, let me change colors here, is found by it bouncing off of your phone or mirror, whatever it is we're using here, and that same vertical line that goes straight up from where it hit. And so if you're sitting in your car and you've got a friend with you and the sun is hitting their phone and reflecting to you, well, the angle that you see from it reflecting, this blue angle that you see here, that is the same angle if you were to go from the phone back to the sun, this direction, okay? And so we have an angle of incidence, that's where the ray is coming into the phone, and then the angle of reflection is where it's coming off of the phone into your face or whatever. And so you can actually sit in your car, and probably on a sunny day you can move your phone screen back and forth, and you can see the sun reflect off the top of your car. And what you're doing is every time you change that phone, you're changing, that you twist it, you're changing that angle of incidence and thus changing the angle of reflection. And so that's something that has happened to most people, and we can see that here. Now, a couple of things that is true about this. When this happens, you have some angles below this phone. If you were to extend that sun ray all the way down here, then you're going to have another angle that would be formed. And this angle is congruent to this angle above it. Okay? And so we have several angles here. And what's important to understand is that the angle of incidence and the angle of reflection have to be the exact same, which means that all the other angles are also the same. So since this is perpendicular, where that line goes up here from our phone, since that line's perpendicular to the phone, then we can know something about this measure, this angle measure, and this angle measure, which then allows us to know some things about the ones below it down here. Okay, that one and that one. And so this angle of reflection and angle of incidence, again, is very, very common. There's some other examples in your book. You could look in the book and section 14.2, and you could see some of those. Now, here's where I've used this a lot in my life. Okay, and this probably doesn't relate to most of you, but when I was a kid, I played pool a lot, and I would shoot pool all the time, and at one point was really, really good. And on a pool table, if I were to hit a ball against this rail, for example, then the angle that it's going to come off of is going to be the same. Again, there's our perpendicular line. This angle is going to be the same as this angle. And so if I'm shooting from down here, well, I can estimate pretty closely to where the ball would hit up here if I were to hit it along that line and hit that rail. And so for me, when I would play pool a lot, I was really good at what's called a bank shot, where you hit it off that side. And I was good at it because I could picture in my head that angle of reflection and that angle of incidence. And you can, if you know anything about pool, you can make it to where it doesn't have the same exact angles. But for this illustration, that's a pretty easy way to see, okay, when I hit that ball against that rail, it's going to bounce off going that direction, and these angles that are formed are going to be the same. And so I knew that if I hit it in the middle of where I'm wanting it to be, then that angle was going to be right. And so there are a lot of applications. Again, we're not going to get into tons and tons of applications here, but I do think it's important that you at least understand that some of this stuff that we're talking about, especially with the reflection, is very, very commonly used in our everyday life. And so notice here we're talking about a ray of reflection. So it's not a line segment, it's not a quadrilateral, it's not a triangle, it's a ray. And so you have the sun ray that comes in, and then it reflects the same exact thing on this other side, but going across that line, that line that is perpendicular to our phone. And so that's what's happening there when we talk about a ray of light. If you have any questions about that, again, let me know. Hopefully this makes a lot of sense to you. So this kind of explains what we were just saying. When a ray of light bounces off a mirror, the angle of incidence formed by the incoming ray and the line perpendicular to the mirror is congruent to the angle of reflection, the angle between the reflected ray and the line perpendicular to the mirror. So again, we talked about that in that previous slide. Now, let's get into another type of transformation that you could see. It is called what we call a glide reflection. A glide reflection is another isometry, okay, just keeping the same shape but moving its location. And what a glide reflection does is it uses a translation where it slides and then also reflects, okay, where it flips over. And so in a glide reflection, what you're going to see is that it's going to slide, okay, so there's the translation, and then it also is going to reflect across a line. And so the original looks same shape and size as the as C3, that image, but it has been moved twice with two different transformations, a translation and then also a reflection. Okay, so it's very possible that you could have multiple of these different transformations that are happening. You could have rotations, and you could have reflections, and you could have translations, really all combined. And so you need to be aware of that as we are continuing on through this chapter. So we can say that if a figure has undergone an isometry, then they are congruent. If we can rotate, or we can reflect, or we can slide an object one way or the other, then we can know based off of that the figures are congruent. Okay? And so our little note here says it's possible to define two figures as congruent if and only if, again, there's that statement, it goes frontwards and backwards. One is an image of the other under isometry or a composition of isometries, meaning that if you can do a translation, or you can do a translation and a reflection, or a translation and a reflection and a rotation, then it is considered to be congruent. Okay, so we're going to look at a couple of examples of that here in this example. Now, we want to take the rectangle that's shown, rectangle ABCD, and we want to describe the sequence of isometries to show that congruence has happened. Okay, so on the first example, we're going to take triangle ADC. So that's this one, ADC. Okay, so you can see that triangle. And we want to show that it is congruent to triangle CBA. So CBA is going to be this one. So that is that triangle. Now, think about how we get from the blue triangle to the red triangle. How do we make the blue one be the red one? If we were to do one of these transformations we've talked about, translations or rotations or reflections, how can we make triangle ADC, the blue one, be the same as ABC, or I'm sorry, CBA, which is the red one? Well, hopefully when you look at that, you realize that if I were to take this and rotate it, take the blue one and rotate it, well then point A would get rotated down here to point C, and point D would get rotated to point B, and point C would get rotated to point A. And so if we do rotate it, do a half turn, so it's a 180 degree rotation, then we would say this one is, it is going to be congruent. And so we're just going to say that a half turn of ADC, triangle ADC, with the center at E. And that's important that we notate that, because we don't want to rotate it around some random point out here, right? We want to rotate it around that point E. That's our turn center. And so when we spin it, we do end up with the same figure. If you have any questions about that one, please let me know. So on the next part, we're asked to show that triangle ADC, so again, that's this one. We want to show that it is congruent to triangle BCD. So BCD is going to be this one. So we want to show that those two are congruent based off of the use of an isometry. Well, if you think about that one, a rotation is not going to work, because if you rotate ADC, you don't get the same shape, right? The same BCD. But if we could flip it, well, that would work. And notice here that in our triangle, we need vertex A and vertex B to line up, right? And we need vertex D and vertex C to line up. And then we need vertex C and vertex D to line up. Because again, when we use this notation of congruency, angle A and angle B need to be congruent, and angle D and angle C need to be congruent, and so on. So the only way that we make the triangle in blue be the triangle in red, or vice versa, is to reflect it. And we reflect it, well, I was going to draw it out here. We reflect it along this line that goes through point E and is vertical. If you flip that one of those triangles across that line, you get the other triangle. And so that is what this says. That is reflection in a line passing through E and parallel to AD. So there's AD here on the left, and so that is parallel to that vertical line that we're talking about, and so it's reflected across that vertical line that goes through point E. Now, what I'd encourage you to do is pause the video, try the next one on your own. Try to see if you can figure out how those two are congruent. I'll give you 3 seconds to do that. Okay, so I'm going to erase what I have here, and that way we can use this figure again. So part C says that we want to take ADC. So again, that's this one, ADC, this triangle. And we want to show that it is congruent to DAB. Well, DAB is DAB. So that's this one, again in blue. And so again, we want to think about, well, how does that red one move in such a way that it becomes the blue one, or vice versa? And so, very similar to the one above it, part B, it can be done by reflection. And that reflection needs to go through the point E and be horizontal or parallel to AB or parallel to DC. Saying either one of those would be fine. But it's through this line that is horizontal and goes through point E. Because again, if you were to flip the blue one across that line, you get the red one. Or if you were to flip the red one across that line, you're going to get the blue one. And so that's what it says here, that it's reflection. If you go across the line that goes through E and it's parallel to DC. We will stop the video here. We will continue, I believe, in section 14.3 in our next video.